We're now going to look at how to complete multiple regression within Excel. But in order to start that discussion, let's look at why we might want to consider multiple regression. Here we have a delivery company looking at how long it takes their employees to complete their work. They've decided to explore the independent variable of kilometers and see if that will accurately predict their time of completion. So let's start by doing our regression analysis. So under data analysis, regression, okay. So here we want our independent variable or our y variable to be our time. That's what we're trying to predict. We want our x variable or the dependent variable to be the number of kilometers. Will kilometers accurately predict the time it takes to complete? Again, because I selected the column headings, I'm going to make sure that labels is selected. And I will have this output on this same page. And looking at our regression output, the one thing that stands out here to me is the r squared value. So I look at this r squared value of being 0.6678 and a whole bunch of other decimals. And if we remember what the interpretation of r squared is that we first convert that to a percent, and then we talk about the variability in the dependent variable that's actually explained by the independent variable we've chosen. Or really another way to think about it, how good of a predictive model are we going to get when we use kilometers as our independent variable? Will that be able to accurately predict the time that it's going to take somebody to drive here? So when we convert that to a percent, we say that 66.79% of the variability in time can be explained by the linear relationship between kilometers driven and time. And again, if we remember, what we're really looking for is an r squared value of at least 80%. When we can get 80%, we've got a pretty good predictive model. Here, with it really only being around 67%, we can say that there's still a considerable amount of variability that's not explained by the relationship between this independent variable, kilometers, and what we're trying to predict, the dependent variable, time. If we're trying to get the equation out of this and make predictions for time based solely on kilometers, it's not going to be a very good predictive model. So what we might want to do is to start, instead of doing a simple regression based on the one independent variable, start adding more independent variables into that model. And as we add more variables into there, maybe we can get a better prediction of how long it does actually take these employees to complete their work. So if we flip over to example 2, it's really the exact same question. The only thing is now, not only has the company decided to explore the kilometers driven, but also the physical amount of deliveries that are going to be delivered on that job. So now, taking into account the kilometers driven and the physical number of deliveries, will that make a better predictive model of the time it will take somebody to complete this work? Anytime we have more than one independent variable, we're now dealing with multiple regression. There can only ever be one dependent variable, only one thing that we're trying to predict, but we can have as many independent variables as we'd like. We're still going to use the same part of Excel to get our regression analysis performed. So under data, data analysis, regression. So here we want to make sure we pick the appropriate y variable. That's our time. Again, the thing we're attempting to predict. Now our x input range is simply all of the independent variables. So now it's not just kilometers. We want to highlight also the deliveries as part of our predictive model. Again, because I've highlighted on the column headings, I will make sure I put labels. Output range, make sure we put that somewhere where we have space. So hit OK. And if we look at this output now, the only spot that's really changed in any way, other than the numbers within it, are we notice, if I go back to example 1, the bottom portion previously only dealt with our one independent variable, the number of kilometers driven. Now down in that final part of the output, we have both of our independent variables, kilometers and deliveries. Other than that, the output looks very similar to what we had before. We should be able to answer all these questions, A through G, based on that output. So in part A, find and explain the multiple coefficient of determination. Don't let that word multiple throw you off. We're going to find the coefficient of determination in the exact same place that we found it when we were dealing with simple regression. So remember, coefficient of determination is our r-squared value. So we have an r-squared value of 0.9161. But as always, it's not the number itself that's the most important. It's being able to say what that number refers to. So our interpretation of r-squared, or the coefficient of determination, is again, we first convert that to a percentage. And we talk about the variability in our y variable, in that thing that we're trying to predict. How much of that can be explained by our, in this case, combined independent variables. So our interpretation of the r-squared of 0.9161 is 91.61% of the variability in time can be explained by the estimated regression equation with kilometers driven and number of deliveries as the independent variables. In part B, asked to explain the value of the adjusted multiple coefficient of determination. So again, coefficient of determination, r-squared. And we have the adjusted r-squared value in this cell right here. Our interpretation of that is very similar to r-squared. But if we remember back to our notes, the difference between r-squared and the adjusted r-squared, which we deal with in multiple regression, is that r-squared can be falsely inflated as we add independent variables. Even if we're adding variables that really add nothing to the model, don't help us make a better prediction whatsoever, they're going to artificially enhance our r-squared value. So adjusted r-squared simply takes into account how many independent variables we have in the equation. So we have an adjusted r-squared value of 0.8921. And as we said, the interpretation is very similar. The only difference is here, this value takes into account how many independent variables there are. So we simply add a little extra to our interpretation and say that after we've adjusted for the two independent variables, now 89.21% of the variability in time can be explained by the estimated regression equation with kilometers driven and number of deliveries as the independent variables. For part C, finding the estimated regression equation and interpreting each of the coefficients. Now remember, we're going to have here three coefficients. The coefficient for the y-intercept, the coefficient for the x1 variable, or in this case kilometers is our first independent variable, and deliveries, our second independent variable, or x2. Really, all we want to interpret is the slopes. The coefficient of the y-intercept is not something we're looking to interpret, as oftentimes it is completely meaningless. But again, we find the values for our regression equation in that last output. So from our coefficients, we can create our estimated regression equation, our y-hat equation. To three decimals, we get a y-hat equation of negative 0.925 plus 0.039x1 plus 0.938x2. So interpreting what those two coefficients of our independent variables represent, remember they're slopes. So we're talking every time our x1 value goes up by 1, y-hat is going to go up by 0.039. Every time x2 goes up by 1, y-hat is going to go up by 0.938. And remember, there's only ever one change we can make in a model at a time. So we don't want to talk about x1 going up by 1 and y-hat. We want to be specific to the data. Interpretation of our first independent variable, or the coefficient of x1, is each additional kilometer driven will lead to an increase of 0.039 hours when the number of deliveries is held constant. We can only alter one of those variables at a time. Similarly, our interpretation of our x2 coefficient would be that each additional delivery made leads to an increase of 0.938 hours when the number of kilometers driven is held constant. Asked to use that model that we just created, our y-hat equation, to make a prediction for the time it would take a driver to make 3 deliveries with a total round trip distance of 100 kilometers. Again, we're simply subbing in our independent variables into that equation. And now that we're dealing with multiple regression, if I want to make a prediction, I need to have inputs for each and every independent variable. Here, since we have 2 independent variables, kilometers driven and number of deliveries, we need values for both of those, which we do here. And we simply sub those values into the equation. So subbing in 100 kilometers and 3 deliveries. For part C, we stated our answer to 3 decimal places just so we could state a final answer. But as we continue forward in parts D, E, F, or further parts of the question, we should always revert back to the full unrounded answers. And what we should get, rounding our final answer for part D to 2 decimal places, we get a prediction. It would take 5.75 hours to complete 3 deliveries with a total round trip distance of 100 kilometers. For parts E and F, now that we're dealing with multiple regression, there are 2 separate hypothesis tests that we have to perform. So we have the F test, which tests the overall significance of the entire model. So whether there's some sort of relationship at all in this model. And if the F test passes, then we move on to the individual tests on each of the independent variables, known as the T test. So we have the F test to test overall significance and the T test to test individual significance. So remember, what we're always trying to determine is always about the slopes. If the slopes are all 0, then there is no relationship whatsoever in this model. If any of those slopes, or all of the slopes, are not 0, then there is a relationship. So the way we express our null and our alternate hypothesis for an F test is we have a null hypothesis that every slope is 0. So if we have 10 independent variables, we've got beta 1, beta 2, beta 3, all those in there, they'll all be 0. There's no significance whatsoever anywhere in this relationship. So H naught, B1 is equal to B2 is equal to 0. Every slope in the model is 0, meaning that there's no significance whatsoever. Our alternative hypothesis is simply that any of those slopes are not 0. It may be all of them, but at least if one of them is not 0, then there is some significance in that model somewhere, which we'll later determine with our individual T tests. So for the F test, overall significance, null hypothesis, every slope is 0. Alternate hypothesis, any of the slopes or all of the slopes are not 0. So again, we were asked to do this test at a 1% level of significance. And where we're looking to find our probability, this bottom output deals with the individual independent variables. Well, here we want to deal with the entire model. And when we're looking at the entire model, we're looking at these top 2 outputs. So if we look here, we have significance F. That is the p-value for our F test. Therefore, the p-value of the F test is 0.00017 and a whole bunch of decimals after that. So since our p-value is less than alpha, we can disregard our null hypothesis and accept our alternate hypothesis. Or in other words, there is something in this model that has significance. There's something in this model which should allow me to make a prediction for that dependent variable we are attempting to predict. So now we know that there is something somewhere in this model that's okay. We've done the F test for overall significance. Now we should go and test each of the independent variables on their own. So we can test if the kilometers driven are significant and they should be left in the model. We can test whether the deliveries are significant and they should be left in the model with the individual T tests. So when we're testing kilometers on its own, our X1 independent variable, we're no longer testing B1, B2, and all the other independent variables. We're only looking at this variable on its own. So is this variable's slope 0 or not 0? And again, we're doing it at a 1% level of significance. So overall test came from our middle output, individual tests now. Now again, we want to go back to our regression output that deals with the individual portion. So we're looking at the p-value here for our kilometers driven. And our p-value is 0.00027 and all those other decimals, which again, we have a p-value less than alpha, which allows me to say that there is sufficient evidence to conclude there is a relationship between travel time and kilometers driven. Now performing our second individual t-test on our second independent variable, number of deliveries. Again, our hypothesis now refer to that we're testing only on the slope of our second independent variable, or beta 2. We're once again asked to do it at a 1% level of significance. Our p-value now coming from the deliveries output. So we have a p-value of 0.026, which again, that p-value is less than alpha. So again, we can disregard H0 and accept H1 and claim that there is sufficient evidence to conclude that there is a relationship between travel time and the number of deliveries. The last thing we're asked to do in this question is to test for multicollinearity and to discuss whether or not it is an issue. So typically this would actually be one of the first things that you would do, because if multicollinearity is an issue, you would want to deal with that issue before we did all the other work that we just did. Remember, what multicollinearity is that when the relationship between the independent variables is too strong, it can actually affect the rest of the model. So if we've taken two independent variables that are very closely related, what could happen as we do our f-test for overall significance, it tells us that there's something good in that model. The model says it's good, so we go and do our individual t-tests, but now the t-tests all come back that there is no significant relationship between any of the independent variables and the dependent variables. What actually happened when we did our test for overall significance, the overall significance found that close relationship between our two independent variables, and the model itself is really no good. So in order to avoid that, really, it is something we should do off the start. If we have 3 or 4 different independent variables, you need to test every combination of 2 of them to see if there's any relationship between any of the 2. But here, there is only the 2 independent variables, so there's only one relationship I have to examine, the relationship between kilometers and deliveries. So remember, testing the relationship between 2 things, that comes from our Pearson correlation coefficient. So here I'm simply going to run a Pearson test. So equals Pearson. And remember, in the breakdown of Pearson, it tells me that this returns the Pearson product moment correlation coefficient, or my R value. So running the Pearson between kilometers and deliveries, we get an R value of 0.15. So where we think that multicollinearity might be an issue is only when that Pearson value is above absolute 0.7. So this is quite a weak relationship, only 0.15. If it was between 0.7 and 1, or negative 0.7 and negative 1, that's when we would consider that multicollinearity might be an issue in this model. If we do have a Pearson value above 0.7, we should remove one of those 2 variables from the model and rerun the entire model. So here it's not an issue. All the work we've done is good, so we can say that since R is less than absolute 0.7, there is no issue with multicollinearity.